Hello, everyone. In this lesson, we would like to talk about the Riemann sum. Riemann sum. The goal is to find the area under a curve. Okay, you look at this picture, and the curve is the blue one, right? This curve is described by the function y equals to f of x, meaning that, of course, it satisfies all the, satisfy the condition for a function. For any input, there's exactly one output. It passes the vertical line test, that is. To find the area under the curve, we have 3 steps. Okay, the first step is partition. So we partition the entire interval from A to B into n subintervals. Okay, we partition it into n subintervals. So subinterval, right? Because the total width of the interval is A to B, from A to B. So the width of the rectangle of the interval is B minus A. Okay, so that's partition, and we partition it into n subintervals. Okay, so let me just adjust it. So delta x was partition into n subintervals. N subintervals. And these n subintervals we call the width. The width, we're going to call it delta x. Okay, so let me find that symbol. Delta x right here. Delta x. Delta x is going to be B minus A divided by n. So each one of these intervals, okay, each one of these intervals okay, and this is a subinterval. Okay, let me make it thicker. Let me make it thicker. Right here. All right, so there's a subinterval over here, and the subinterval over here, another subinterval, so we have n of them. We have n of them. So let's see, how do I make them thicker? This is how I make it thicker. Okay, so this is subinterval, and that's another subinterval, another subinterval, right? So each one of these subintervals has a width, How wide they are? Delta x. And delta x is b minus a divided by n. And we have n subintervals. For each one of these subintervals, okay, and we're going to approximate the area by a rectangle, So the subinterval description is A to x1, x1 to x2, x2 to x3, xi minus 1 to xi, and the last one is x sub n minus 1 to b. So for each one of these subintervals, of course, we have S1, S2, S3, Si, Sn. These are sub-areas of the area under the curve. And to find the area, right, under the curve, we use approximation. So let's look at the next picture. For the first subinterval, we're going to use, we already have the width. That's how wide it is. That's a delta x. How high it is, right? We're gonna pick a height, and the height is picked by selecting any point between A and X1. For example, when we consider the first sub-area, we pick X1 star as the input and the height, right? So this height, which is, let me write it down. That height is, okay. That height is F, whoops. Let me write it down. Let's write the curly. Okay, here we go. So the height is F of X1 star. Okay, I cannot write it the way, okay, let me try it this way. Okay, you know what? Let me just use pointer. Let me use pointer. So this height is F of X1 star. So this is the piece. F of X1 star, that's the height of the first rectangle. So this area, okay, so this area is used to approximate the area under the curve for S1, okay, and this is the height, and this is the height. On the picture, of course, you see the broken, you see this is F of X1 star, okay, so let me use X of X1 star here. There. So this piece, okay, that's F of X1 star. F of X2 star, F of X3 star, right? And this is F of Xi star. Okay, this is better. Okay, so once we have the height of the rectangle and we have the width of the rectangle, which are uniformly the same as delta X, and the height multiply the width, that's the area of the rectangle. We have the area of the sub-interval, we have the sub-areas of the areas underneath the curve. So this is S1, right? This piece is S1, S2, S3, and SI. We call this a typical slice area, a typical slice. And this is the last one, S sub n, okay? And that's the partition and the construction, and then it leads to Riemann sum. Riemann sum is to add all of these approximated areas. Okay, this piece, S1, right? So let me put all of these areas right here. Okay, so that's the area S1, and that's S2, SI, right? And S sub n. You can see that each one of the areas is approximated, and we add them up. We add them up. So area 1 plus area 2 plus area I, and remember how the typical slice is described. The typical area is described. Well, you're going to use the word typical in both Calc 1 and the Calc 2. So finally, we got the Riemann sum. We got the Riemann sum. And the last step, okay, the last step is taking limit. Okay, so partition, a construction of Riemann sum, and taking limit. We take limit of Riemann sum. We take limit as of Riemann sum And the limit is described as following here. Okay, limit as the number of subintervals approaches infinity, and we take limit of the Riemann sum. If this Riemann sum has a limit, right? So if this limit exists, and this limit is called the area under the curve. And the other way to take this limit is described in the following way, is approaching as delta x approaches 0. So there's another way to express this, is delta x, okay, approaches 0. If this, well, these two are actually the same thing, because as n approaches infinity, delta x approaches 0, because they have this relationship, right? Remember at the beginning, we have this description, right? So as n, in this relationship, as n approaches infinity and delta x approaches 0. Okay, so you can use either one, which means that the partition is getting finer and finer and finer. Okay, so that's what Riemann sum is all about. Take an example. Let's take an example. Okay, this example is to say, well, we pick any points in between this, the typical interval, right? So this time we pick the point which is just endpoints, right? Suppose we pick the endpoints, and well, let me put this notation there. Okay, so if this limit exists, we also use a notation, right? If the limit exists, the notation is such. Okay, so this describes the area between A and B under the curve, right? So for example, when we try to find this Riemann sum, we can pick any points in between. We can pick, say in this example, we let's take a look, right? Let's take a look in this particular picture. What do we see? We have these subintervals. So I'm gonna copy this, what we did earlier, right? In this example, in the subintervals, what do we have here? And look at from the picture, right? The sub-areas. In the first area, it looks like we use f of x1 as the height, right? So f of x1 as the height, x sub 1 as the height, and the area is delta x. Okay, so multiply delta x. And the second sub area, we use x sub 2 as the height of the rectangle. And so that's f of x2. So we use the endpoint, x sub 2, and multiply delta x. Okay? And keep going. For the i's subintervals, look, we use f of xi as the height. So this is going to be f of x sub I as the height and multiply delta x. So these are the sub areas. And the last one, last but not least, we use B as f of B as the height. And that area is f of B multiply delta x. Now the question is, can we do that, right? Of course. It is proved, right? If a function is integrable, it doesn't matter which point you choose as x1 star, x2 star, or x3 star. You can pick any point. You can pick a point on the left. You can point on the right. You can choose any point in between for any interval, and the limit is going to be the same. This kind of property, if this is, integrable functions all satisfy this situation, and therefore we call the definition of a definite integral. Okay, so let's look at the definition here. Okay, if f is a function defined for from a to b, divide subinterval, and x sub 0 is a, x sub 1, x sub 2, x sub n is b, be the endpoint of these subintervals, and we have x1 star, x2 star, all the way to x sub n star, be any sample points on these subintervals. If so, xi star lies in the I subinterval, then the definite integral of f from a to b is defined as such, provided the limit exists. Okay, and it gives same value for all possible choices of sample points. And if it does exist, we say that f is integrable. So for any integrable functions, it doesn't matter which point you choose as xi star, limit is going to exist and it's going to be the same. Okay, so in this particular situation, what we need to learn is that kind of function we find the area underneath the curve look like this, right? Let's look back. On the A side, on the B side, they're straight line, they're vertical lines. So on the other side, this is the interval, it's a straight. So we have three straight lines. A, f of A, B, f of B, and between A and B, the three-sided straight line, and there's one-sided curve. So our Riemann sum can find the area underneath the curve if the function is integrable. So we construct the sub areas and add them up, get Riemann sum, and take limit. If limit exists, that's the area underneath the curve. A typical slice, a typical area, you're going to hear these words over and over again in Calc 1 and especially in Calc 2, that this typical slice is constructed in the following way. Okay, it's the I's interval. The I's interval. Okay, let me draw a little picture. The I's interval, right? This is the I's interval. I'm gonna make it thicker. Okay, the I's interval. And here's the height. Okay, let me change the color. Okay, and this is the height, or any height you've chosen. And the area, the area underneath the curve is approximated by this rectangle. And this is called a typical slice. And this typical slice is the height, f of x sub I star, right, times delta x. In this case, in this example, is f of xi, okay? So let's go back to see our more general case. the typical slice. Okay, we want to remember how to construct that typical slice. That typical slice is constructed okay, the typical slice is constructed. So here is the typical interval. Okay, this is the typical interval, delta x. The width is delta x. And the typical height, okay, this is the typical height, the blue. Okay, we pick any points inside this typical interval between x sub I minus 1 to xi. We call it xi star. Xi star, we evaluate the function's value f at f of xi star is f of xi star. So this is the function value. So this is the height of the rectangle, and this is the width of the rectangle. And here, this is the typical slice. This is the typical slice, okay, which is right here. This is a typical slice. Once we know how to construct a typical slice, and we got the sum, which is a Riemann sum, and then we take limit. Okay, all right. Okay. And next, we got a theorem. We got a theorem here. The theorem says if f is continuous on a closed interval, or if f has only a finite number of jump discontinuity, then f is integrable on interval a to b. That means the definite integral all exist. And this theorem, basically, you just choose the endpoints. You just choose the endpoints. So choosing endpoints is a typical way we do the actual calculation. In a different video, I will be going into the details. But in this example, we just talk about the ideas. Now, let's look at some other situations. For example, we have a curve, right? And the curve goes, up, down and up. So some area actually is negative, some area is positive. So now we could have positive area, negative area. So the total area, there'll be some cancellation taking place. Okay, so in the future, we're going to see some more examples of this sort. All right. So once again, to summarize Riemann sum, 3 steps: partition, construction of Riemann sum, and taking limit. Most of the functions we're dealing with, piecewise function, continuous function, they are all integrable. So we can always find, Riemann sum, we can always find the limit and the area underneath the curve. All right. Thank you for watching.